Okay, I think I updated the website, Canvas, as well as added a couple videos to Top Hat. I'll send out a link or an email this afternoon that'll have a take-home quiz for Wednesday on chair cyclohexanes, and it'll also have a listing of when the chapter 6 or chapter 5 stuff will be due. So I think tonight chapter 4 homework problems are due, I think. So it's chapter 5, and technically we're finishing chapter 5 today. So that means, well, it means probably, we would mean like Friday, the in-class readings due, and then on Monday, because there's no class on Friday. So I'm going to make both those due on Monday for chapter 5, the in-class and the extra problems, and the homework problems. So they'll all be due on Monday, but I'll confirm that. Okay. We left off, I think we talked about the stabilities of the 1,2 dimethyl cyclohexanes. And so the rule is that you want the groups to be equatorial, and you want the groups to be both equatorial if possible. So let's do one more here, and let's do something like, let's do 1-ethyl 3-methyl cyclohexane. Okay. So can you draw the 4 different conformations, chair conformations of cyclohexane for this molecule? Then tell me which ones are cis or trans, and then tell me their rankings from 1 to 4. Okay, so the first thing that we need to do is we need to decide your number 1 and number 3. I would use this. I always use that as number 1, and then, bless you, then that would be, so there would be the 1, 3. And it really doesn't matter what you choose as number 1 as long as you get the other group into the 3rd position, wherever that is on the ring. All right, so then let's put ethyl groups. We'll make 2 ethyl groups axial, and then 2 ethyl groups equatorial. And then we can alternate the methyls so that in each case we've got the 2 combinations. So for number 1, ethyls axial, methyls axial, ethyls axial, methyls equatorial, and then methyl axial, ethyl equatorial, and then finally for the last one, both the ethyl and the methyl equatorial. So there's our 4 conformations. So let me just double check here. attendance. I don't want the whole thing. Question. Okay, so tell me which two are cis, and just type in both letters. So I've got this set up as a word answer, but all you have to do is type in the two letters for the ones that are cis. All right, going once, twice. Okay, so it looks like most of our answers are A and D. So, all right, so A is cis and D is cis. Okay. Both methyl groups here above the plane of the ring. Both alkyl groups here on D below the plane of the ring. And again, if you're uncertain about that, this hydrogen is above, that hydrogen's above. That makes those two below. So use the hydrogens as a point of reference. That makes the other two then trans. So first thing I'm going to ask you to do is identify cis and trans. Okay. Right. Any questions about that? So then my next question would be, what is the most unstable structure? A, B, C, or D? But what I should do is I should ask, are there any two molecules that have the same energy?
B and C do.
Are we sure about that?
Would C be slightly more stable because it has the larger group and that's the total?
Yes, but that doesn't get at the question of what they do have different energies. If you have different groups in the axial positions, they're going to have different energies. So having a methyl and an ethyl is not the same as having two methyls. So these will all four have unique energies. So none of these have the same energy. Okay. So then my question would be, and let me just go ahead and ask you to do this, but I'm going to have to ask you very specifically how to put in your answer. What I'd like you to do is go from most to least stable, and put all four letters, no spaces in between them, in a row in lowercase letters. Okay, so lowercase letters, A through D, from most to least, no spaces in between them. And if you want to choose your own formatting for this, then I guess it's going to show up by itself. But that's the way I would like it. All lowercase, no spaces, from A to D, rank them in overall energy. And since there's no ties, each one has to have a unique energy. Okay, do I have an answer from everybody? Okay, that's fine.
Yeah, that was.
All right, the most popular answer is D, then C, then B, then A. Don't change your answer in the middle of the... Stop. So it's D, then C, then B, then A? So D is the most stable. We agreed on that? Most of us are agreed on that. Why? Because both alkyl groups are in the equatorial positions. All right, the next most stable was C. And so the difference between B and C is one has a methyl group axial, one has an ethyl group axial. And in this case, just like we had for our Newman projections, the bigger the group, the more unstable the interactions. So when you have a methyl undergoing 2,1,3 diaxial interactions, that's not as destabilizing as having an ethyl group. So in general, the bigger the group, the more destabilizing it is to have that large group axial. So given a choice, you want the small group axial first, and then for the other conformation, having the larger group axial will be less stable. Bobby?
So C is the second most stable.
So C is the second most stable, and then B would be number 3. So most is A, or most is D, then C, then B, and then finally A, because in A, both of the alkyl groups are axial. And in this case, because it's 1,3, they're not only going to be having 1,3 diaxial interactions with hydrogens, they're going to be having them with themselves. And so that's going to be a huge issue. Okay. So, bigger the group, the more unstable when you put it axial. Okay. Does that kind of make sense to everybody? So then for the take-home quiz, I will give you a molecule and I'll ask you to do the same thing. Write it out, and you've got to write the structure I give you. Okay? And if you give me, your own molecule, I can't grade it because I don't have an answer key for it. Right? I'm sort of being facetious there, but what does that mean? It means you still have to remember your alkyl groups. Because if I give you a 1-tersh butyl 3-isopropyl group, you're going to need to know what the tersh butyl group is, what the isopropyl group is. Because if you give me something else, that's not the problem I gave you. All right, so you're going to, at best, maybe get half credit. So you want to write the molecule, and so you still need to know your alkyl groups. Okay. So I'll ask you for that. I'm just going to I'll send you the actual thing. You can print it out and then you can write on it. Okay. So this is the important part of cyclohexanes. The other thing we need to be able to do with cyclohexanes is that we need to convert from chairs to flat cyclohexanes and vice versa. Okay, so for instance, if I asked you, can you convert this dimethyl cyclohexane into a flat cyclohexane with bold and dashed wedges, could you do that? So the first thing we have to do is figure out a numbering scheme, which I would say goes there. If you go counterclockwise around, or clockwise in this case, around the ring, then you would want to go clockwise around this ring. It doesn't really matter where you start with, where the 1 starts. In my world, number 1 is here, and number 1 is there. But you can you can live in a different world. You just have to make sure that in this case, the 2 groups are 1, 3, that they are 2 positions away from each other. Okay. So if I did that, what should the methyl group go on? Should it go on a bold wedge or should it go on a dashed wedge? And then let me give you perspective. My perspective is always, I'm above the ring looking down on it. So where should the methyl group go? Number 1. Where should the methyl group on 1 go?
Sydney Sello.
Sydney.
You do a dash wedge.
Dash wedge. Do we agree with her? Why?
Below the ring.
Because this methyl group is below the ring, and so that would put it on a dashed wedge if we're looking at it from above the ring. And the other thing with rings is when you have two in the plane, there's always a bold and a dashed wedge. So if the hydrogen's not shown, it's on a bold or a dashed wedge, whichever one is left over. Okay. So on carbon 3, where should the methyl group go?
Follette.
Bold wedge, because that methyl group is it's above the plane of the ring. So let me just caution about a couple things.
Does it matter when you put so the bolded wedge and the dash wedge on 3? Does it matter which one's on the left, which one's on the right?
No. Because you know what? They should be right on top of each other where you can't see the hydrogen.
Right.
So it doesn't matter whether you put it on the left or the right. And that's going to be important in the next chapter. So let me just say axial and equatorial are different than cis or trans. Cis or trans you're going to get from whether the groups are both above, both below, or one of each, in terms of above or below the plane of the ring. In this case, this molecule is what? Cis or trans? It's trans. Now, if I went back to the last molecule and looked at trans, which I'll do, the two trans were actually one axial, one equatorial. Oh, because this one was a 1,3 diaxial interaction, or 1,3 substituted. Let me go to this morning's where we did 1,2, and in this case the trans is either both axial for 1,2 or both equatorial for 1,2. So the issue here is that sometimes people will try and say, oh, well, they're both axial, therefore it's either cis or trans. Well, if you're going to remember it that way, you've got to memorize whether they're 1,2, 1,3, or 1,4 disubstituted, because it switches as you go from each position. So my suggestion is don't use up that much space in your brain, because you might need it for other things. Just begin to kind of see, okay, above the plane of the ring, below the plane of the ring, trans. Because that way you don't have to memorize 6 different combinations. But there is, cis and trans is different than axial and equatorial. In this case, it's trans because the one methyl's above, one methyl's below. Not that one's axial and one's equatorial. Okay. So you have to be able to go from this to this and from chairs to flats. So flat cyclohexanes. We'll have to do that in the next chapter. Right? Any questions? So it'll be a take-home quiz. It'll be due Wednesday for that. So that means we're done with chapter 5. So now we can move on to chapter 6. And fortunately for us, the first half, or first third, I guess, or first quarter of chapter 6 is review, because it's cis and trans and E and Z. In particular, they now have more details on how to do E and Z. Like, how should you evaluate a carbon-carbon double bond? How should you look at a carbon-oxygen double bond? How should you look at a carbon-carbon triple bond? Well, we don't need to do that because we already did that. So we can use the Kohn-Ingle-Prelog sequence rules to rank two groups, higher or lower, based on what the groups that are the atoms that are attached and what's attached to those atoms. And so we don't have to spend any time. I don't have to spend any class time going back over that, because hopefully you know that, and if you don't, and if you need to review, you can go ahead and review it. And you'll review it by going through the problems, and those problems should be pretty straightforward. But what we really want to do is we want to apply that now to what are called stereoisomers or stereochemistry. So if we take a look at all of our different stereoisomers that we know about to date, we have cis-trans stereoisomers if we have a double bond, or if we have a ring. We know about cis-trans stereoisomers. And these ones cannot be interconverted. Right? I have to break a bond to make the cis the trans and vice versa. So then we have conformers, which are a type of stereoisomer. And conformers were our Newman projections, whether something was staggered or eclipsed. And so we've talked about those. Conformers you can get by you can interconvert them by rotation around the single bond. The next type of stereochemistry that we're going to talk about in Chapter 6 deals with having molecules that are mirror images of each other. So here's two molecules that are mirror images of each other. And we'll get to the exact terminology of what these are called, but for now they're mirror image isomers. And this is probably the most important type of stereochemistry, because it doesn't seem like much. But when molecules have these carbons that have, number one, 4 different groups attached to them, which means that they're sp3 hybridized. When you have 4 different groups attached to a carbon, that makes it what we'll call a chiral carbon. And chiral means handedness. So this is the handedness of the carbons. You have a left hand and a right hand. But the molecule has to have a chiral carbon in it. And a carbon is chiral when it has 4 different groups attached to it. An alternative definition is that there's no mirror plane that passes through that carbon. And I'll give you a couple of quick examples, and there's more in the textbook. So either one of those definitions for a chiral carbon, and for a molecule to be chiral, it needs to have at least one chiral carbon. So there's going to be 2 dimensions of handedness. One at each carbon's level, and overall at the molecular level. So we can have 2 molecules that are left and right-handed forms, but they may contain 1 to 20 different chiral carbons. But they have to contain at least 1. Now, why are these important? Well, we're going to talk about the physical differences of chiral molecules and chiral carbons on Monday after break, because I have a canned lecture that I do after fall break, so you don't have to watch any videos not that we're having videos, but so I'll talk about the physical properties, but the chemical properties are sort of analogous to what happens with gloves. Okay? Mirror images, non-superimposable mirror images, my hands. But I've got to compare them this way. It's not fair to compare them this way. They got to go this way. So mirror images, non-superimposable. They're chiral. I can't pass a plane through my hand and make the left hand and the right hand the same. If I had no thumb, questionable. I might be able to do that, but the thumb causes that to be a problem. So these are chiral. Do we have chiral gloves in the lab? Is there a box of left-handed gloves and a box of right-handed gloves? No. So the gloves in the lab are achiral. And if I pulled them out and I laid them on the table, there would be a mirror plane that cuts through the center of the glove that makes that achiral. If I held them up, you'd say, oh, well, that's easy enough to do. Then I can flip them over like that because they don't have a back and a palm. So you just flip them over. Okay, they're superimposable. Either of my hands will fit in either of those gloves, any of those gloves, because my chiral molecule is interacting with an achiral molecule. My chiral hand is interacting with an achiral glove. You could do this with shoes as well. What happens when wintertime comes and I have to break out the winter gloves? There is a left and a right-handed glove, right? Because the thumbs move down. And there's no mirror image. There's no mirror plane through the molecule. So trying to fit a left hand into a left-handed glove is easier than trying to stick it into a right-handed glove. When two things are chiral, there's going to be a preferred matchup. Same thing's true for molecules. When I have a drug molecule that's chiral, it's going to interact differently with two different chiral molecules. And we're made up of nothing, well, we're not made up of nothing but chiral molecules, but we're made up with a ton of chiral molecules. From amino acids, proteins, enzymes, sugars, they all exist in one form in the biochemistry in our bodies. And so drug molecules will interact differently with those chiral molecules. And so in drug design, if you have a molecule that you could make one form of, you have to be careful with that. There's some good examples. You take an Aleve tablet. Aleve has, and we're going to take the components out of an Aleve tablet later in lab, but an Aleve tablet has one chiral molecule in it, a molecule of one form. And the one form cures my headache, the other form probably do some liver damage. So hopefully there's just that one chiral molecule in my Aleve tablet. And there better be in order for it to come on the market, at least in the US. Because chiral molecules have to go through a ton of stuff. You have to show that they don't change form in the body. You have to show what the other one does, that it doesn't change into that, like when it gets to your stomach, that other one doesn't have some sort of beneficial property that you're excluding it. Yeah, I could never figure that out myself. Why the FDA was like, okay, well, but the other one could be good too. Well, so what? I mean, we're interested in it not being bad. There's an ibuprofen you can take that'll cure your headache in 20 minutes versus an hour for the 50-50 mixture. The purple pill that used to be on TV a lot, I think it's Nexium, that's a chiral molecule. dopas, and there's all of these molecules that exist in one form or another. In the 60s, there was a drug called Follette Amide. And it was the first case where the chiral centers really came into play because it was a sedative for pregnant women. One molecule acted as the sedative, the other one caused birth defects. And they didn't know that until the first babies came, and then they realized that that the mixture of the two drugs was not good. And don't Google that stuff, because they're pretty horrific birth defects. But then it's back on the market. It's like one of the top 100 drugs that are sold because they are selling only one form. Now, my chemical company would not be selling that drug because my legal team would have said, "Are you out of your mind?" Because what if it metabolizes in your body to the wrong form? What if the lawsuit potential would be huge? If you're just into the money, the human factor would be huge. But it is on the market, and it probably has a disclaimer that's like 3 commercials long, because you know how it's always the fast talking, this causes this, diarrhea, this. It would probably, the whole commercial would be like, don't get in the same county with this drug if you're a woman. And so it's there, but it's the most egregious example of how these drugs, how one can really do something bad and the other one did something positive. So after that, chiral drugs get a lot of scrutiny. But you buy an Aleve tablet, even at Walmart, CVS, it's all the same. It's all chirals, we'll find out. So when drugs interact with other chiral molecules, they will react differently. In your essential oils, and when we made our clove oil, I don't think there were any chiral centers in that molecule, any chiral carbons in any of its components. But in lavender, I'll talk about Monday, there's one molecule that it can exist in two-handed forms. And one has one sort of description of its smell, and the other has a different description of its smell, which means that we have chiral receptors in our nose that can tell the difference between those two forms. And so in like perfumery, in essential oil, having the right mixture of enantiomers is important. It's not life or death, but it's important for creating whatever fragrance you want to create. And we'll talk more about that and the physical properties behind them. So this is an incredibly important topic in terms of knowing what form we have. And it actually is as simple in the molecular level to say, I either have the L form or the D form, because I have the levo or the dextro, which means left and right. But we'll get to the physical property that's responsible for that. What I'm really interested in is, how do I tell the exact three-dimensional structure of that molecule around that carbon? So for instance, if I have 2-bromobutane, my question would be, number one, I think that's a chiral center. I think that's a chiral carbon. Now, the first rule is the carbon has to have 4 different groups attached to it. And it has to be sp3. So that leaves out a ton of things. Double bonds, triple bonds, CH2, CH3s. So if I'm looking at this molecule, CH3, not chiral. CH2, not chiral. CH3, not chiral. This carbon, methyl group, ethyl group, hydrogen, bromine, 4 different groups attached. So that's a chiral carbon. So that means there's 2 ways I can orient that molecule into a left and a right-handed form. When we go to rings, if I had that molecule, how many chiral carbons are there in that? It turns out there's 0. Why are there 0? Well, because all the CH2s got eliminated, but this is the last one. I got a chlorine, I got a hydrogen. Then I've got a CH2 and another CH2. And this is where the E and the Z Coningal Prelog sequence rules come in. It's not just a CH2 and another CH2. What's attached to this CH2? Another CH2. What's attached to this CH2? Another CH2. They're still tied, and then I get to the same point. This entire group was the same as that entire group, so that carbon only has 3 unique things attached to it. 2 of the groups are the same. It ain't chiral. Okay. Plus, I could use my mirror test. Can I pass a mirror plane through the molecule and go through that carbon? Yep. Now you might say, but the Cl is on one side and the H is on the other. Oh no. The Cl and the H, they're right on top of each other. So that mirror plane cuts through cuts the Cl in half and the H in half. Because we just saw in cyclohexanes, they're axial and they're equatorial, but there is a plane. But I could say, let's make a different cyclohexane. And so let's put 2 chlorines on there. And not everything with a bold and dashed wedge is going to automatically mean that's a chiral carbon. But in this case, I would now make 2 chiral carbons. There's no mirror plane that cuts through any of those 2 carbons that cuts the molecule in half. Now, if you're saying, well, there's a mirror plane that cuts the molecule in half, yes, there is, but it doesn't go through either one of those 2 carbons. And if I wanted to just use my 4-group test, chlorine, hydrogen, CH2, not CH2. So I've got 4 different groups. So, first thing is being able to identify chiral carbons. And I'm sure there's questions like that in the book, as well as I think I put some links. If I didn't, I'll put some homework problems that I have from the past where you just go through and find them. But the first thing we have to do is find the chiral carbons in the molecule. And we're going to start with straightforward ones where there's just 1. And then we'll make it a little more complicated maybe on Wednesday. Okay. Right? So we got to have a carbon with 4 different groups in order to have this left-right handed phenomenon. But I can't tell if I had this 2-bromobutane and I had it in a chiral form. I can't just say to another chemist, oh yeah, I've got that in my left and right-handed forms. Although I will. I'll tell them it's either levo or dextro. But that doesn't necessarily tell me anything. What I'd like to know is, if I wrote that carbon 2 out in a tetrahedral format, and I use my methyls and ethyls, which the book is now using routinely, which I'll just use here to save me a little bit of time. What's this exact 3-dimensional structure? Now, the exact 3-dimensional structure of that carbon is called its configuration. This is the exact 3-dimensional structure of a chiral carbon. And there's 2 letters that we use to designate that. It's either R or S. Every single chiral carbon has to get an R and an S description. And that tells you whether it's one way or the other way. And R stands for, I think, rectus, and S stands for sinister, which is basically some Latin terms for something. I don't know. My Latin's not up to speed, but it basically is what they decided to use as descriptors. Okay. So how do you determine whether it's an R or an S center? Well, rule number 1, first step, I want to rank these 4 groups from 1 to 4 according to the Coningle-Prelog sequence rules. And usually, this is the point where we first introduce the Coningle-Prelog sequence rules, but you've already been introduced. Now, whether you had a good or bad introduction, you've got to make it better. So we need to know that. So what would be group number 1? BR would be number 1, because remember how I do this, and this is where the ethyl and the methyl are meaningless. Let me write the groups out, because I'm going to need to do that. So I've got bromine versus hydrogen versus carbon versus carbon. So now I'm looking at the atoms that are attached to the chiral center. So bromine, or we're looking at those atoms, highest atomic number wins. Bromine number 1, hydrogen number 4. Hydrogen's always last. And even if I put a deuterium, a hydrogen with a mass of 2 on there, it still beats hydrogen. There is nothing lower than hydrogen. All right, then methyl or ethyl. Well, that's not good. They're doing experiments on people. I don't think we have that kind of IRB format here. Methyl or ethyl? Ethyl number 2 and methyl number 3. Okay. That's step 1. Okay? So you need to know your Coningle-Prelog sequence rules. Now, what's step 2? Well, step 2 is to point the lowest priority group away from me. And if you can imagine this tetrahedron looking something like a steering wheel, a very old steering wheel, where the number 4 group is like away from me, I want to orient it so 1, 2, and 3 are like in a steering wheel. That's the old steering wheel analogy that we use. My rule is, let's put the 4th priority group on a dashed wedge. And if it's on a dashed wedge, by definition, it's pointing away from me. Okay. So that's the second step. Oh, in this molecule, I already gave it to you like that. What happens if it's not like that? Wednesday. We'll go through some of the possibilities. So when it is away from me, now what's R and what's S? Well, if I draw a circle or if I draw an arrow from number 1 to number 2 to number 3, and it goes clockwise, that center is R. So once the 4th priority group is away from me, if going from 1 to 2 to 3 is clockwise, it is R. If, on the other hand, it was counterclockwise, then that would be S. So this is how we determine the R and the S configurations, is by ranking, orienting the molecule so that 4 is away from me, and then is 1, 2, 3 clockwise, or is 1, 2, 3 counterclockwise. Okay. And the toughest part of this, well, there's several tough parts, but getting the 4th group away from you might be a bit difficult. So what we'll do on Wednesday is I'll give you some ideas. There's one method that I use that's probably a little controversial because the only place I can find it is in Organic Chemistry for Dummies version 1 or volume 1. There is a chapter in there called Stereochemistry for Dummies, which I've put in the folder, and only because it's the only place that documents what's called group switching. And I don't know where I learned group switching. It's nothing new, but it's something that most organic books will not show. I haven't looked at Top Hat yet to see if they allow it, but I'll explain why it's like underground on Wednesday. Okay, so I'll send you your take-home quiz. It'll be due at the beginning of class. If you have any questions, email me or come see me. Otherwise, I'll see you on Wednesday. If you didn't get your exam, you'll have to stop by my office to get it.
I have to fill out a progress report for baseball.
Okay.
I just put the exam grade in there.
Yeah, because that's you're at higher than that, but okay.